Hi, everyone.
Hey, good morning, Kate.
Morning.
Morning.
Morning, Alina. Let's give it a couple more minutes and see if more people join. Now we can get started.
Sounds great.
All right, I think we don't have a lot of people, but we can get started. If some other people join, they can look at the recording and they can participate then.
Sure, that sounds good. I can go ahead and present my screen just to provide some context. Ricardo, you reached out over an issue on Ocari, kind of inviting us to come here and present.
Yeah.
And so, yeah, I'm excited to kind of share an overview of Ocari. And Yurka, one of the original architects on Ocari, is also here and can answer questions as we go.
Awesome. Yeah, excited to have you here.
Yeah, and what motivated y'all to reach out? We just got accepted into the CNCF. I don't know if that kind of brought you all our way or if you found out before then or heard about us.
Yeah, so that was one part, and the other part was we had a presentation from K3S, and they mentioned that they wanted to use you or integrate with you in some area. So then I looked up the project, and then I looked at it got accepted into the sandbox CNCF. So then I decided to open the issue.
Yeah, awesome. Well, yeah, we've definitely been talking to them a bit to the SUSE folks in general about collaborating. So that's exciting that there definitely seems to be some momentum on that conversation.
Mm-hmm.
Well, great. I'll go ahead and kick us off. My name is Kate Goldenring. I'm a software engineer at Microsoft, working on an open source project called Ocari. And to kind of get us started, I just want to talk about who else is involved here. Yurka, who's on the call, like I mentioned, one of the original architects. And this is also some of the other maintainers on Ocari. And we are all currently at Microsoft, all the maintainers. There are, of course, contributors from the larger community, but these are some of the key figures here. What we're going to talk about today is we'll talk about what Ocari is, some of the motivation behind it. We'll look into an overview of its implementation. I'll show you a demo, and then finally we'll end with a roadmap.
Sounds great.
So what is Ocari? So it's an open source interface between Kubernetes and constrained devices. So think MCU class devices that have one fixed function. It could be more CPU intensive devices, but those are kind of the ones we're focusing on. And it's a Kubernetes operator that discovers these IoT devices, whether they're locally attached to Kubernetes nodes, embedded in the nodes themselves, or across the same network. And what Ocari does is, after discovering these devices, it will create Kubernetes resources to represent those devices using the device plugin framework. And upon discovering the devices and creating resources for them, Ocari will automatically deploy pods to use those devices. And just a recent update on Ocari, we were accepted into the CNCF as a sandbox project as of September 2021. Kind of going into that what a little bit more in detail. Like I mentioned, we discover the IoT devices, but one thing that in particular is unique is that on the edge, these devices sometimes have intermittent connectivity. They may come and go, they may break. You may scale up your deployment of IoT devices. Ocari handles all these scenarios unique to the edge. And what it does is, like I mentioned, connects them to the clusters and brings them into the cluster as a Kubernetes resource. And we also have automatic ability to use those devices with our controller. And we really architected Ocari with extensibility in mind. So the way that Ocari discovers devices is via our discovery handlers. And we currently have 3. So OnVIF for discovering IP cameras, OPCUA for discovering industrial machinery, and UDEV for discovering devices in the local Linux device file system, such as USB thermometers, GPUs, etc. But our discovery handlers are just an implementation of a gRPC interface. So anyone can create one to discover their unique devices. It could be even some proprietary protocol devices that you want to discover. Any of it, you can implement that interface and extend Ocari to discover even more devices. And we'll talk a little bit about that process more in detail later. Originally, we were a part of JS Labs with other cloud native open source projects such as Helm started there as well. And now we're moving over to the CNCF. And since we are focused on these edge scenarios, we built Ocari in Rust to kind of optimize and be as low footprint as possible. To talk about the motivation behind Ocari. So Kubernetes traditionally is used in the cloud, where the servers and nodes are very homogeneous. You have the same hardware in these server racks in the cloud. But on the edge, not only are these nodes themselves varied, they could be Raspberry Pis, Intel NUCs, server class hardware on the edge, doesn't matter. Those themselves are varied, but also the devices around them are varied. So you have all different types of IoT devices that they can see and ideally use. However, these devices are oftentimes too small to run Kubernetes. So like I mentioned earlier, MCU class devices don't have enough compute to be nodes themselves. So how can these devices be dynamically leveraged by Kubernetes workloads? How can they be used and effectively added to the cluster? And our goal with all of this was to create a standard way, open source way to connect IoT devices to a cluster, which is why Ocari stands for a Kubernetes resource interface. And because we're focused on the edge, that's why Ocari means edge in Greek. When we talk about the motivation behind Ocari, we like to go through a scenario, a typical IoT scenario that you could do today without Ocari, and then talk about how it could be improved with the benefits of Ocari. So in this scenario, let's say you're a farmer, and on your farm, you have a bunch of chickens, and you've run into a problem where your chickens keep getting eaten by coyotes. So you decide to set up an IoT scenario where you set up some IP cameras, an ML inferencing workload that will detect the coyotes, and then ultimately some application that will alert you to go out and scare away the coyotes. So you could do this all directly from the cloud. And say you took a microservice approach, you could deploy a frame server pod to use each individual camera, grab the video frames from that camera, pass it off to some inferencing pod that does the ML inferencing to detect those coyotes. And then that pod will ultimately send the output to some alerting pod that will tell you to take action. this is all doable, but farms are in remote areas. There may be some latency issues here. So say you decide to follow the laws of data gravity and process your data closer to where it originates. So you set up a node on the edge and you decide to add it to a cluster because you're optimistic about expanding your farm. Maybe you add a field or two. And so you want to be able to add more nodes later on. So the same deployment could happen here. You deploy a frame server to use each camera. But if we look a bit more into the details of what's happening here, that frame server, you have to configure it with a specific RTSP URL for the specific camera it needs to connect to. So you have to first of all discover and know that device is there, and then also configure the application to use it. And so on the right here, we're keeping track of all the steps that an operator needs to take. So you have to do that for each of the cameras. Then you have to deploy the inferencing pod to use the GPU. And then say things start to change. We're on the edge. Say the camera errors or it breaks or goes down. Well, that frame server pod's erroring or is idle. So you have to either bring down the camera, fix it, or bring down the pod. Say you want to scale up your IoT device deployment, add 1, 2, 3 cameras. Well, you need to then go deploy those pods and configure them to use those devices. Say you decide to expand to that new field. Well, you have to go ahead and deploy a new inferencing pod. So as you can see, as the environment would continue to change, you'd have to continue to react. And that's where Ocari comes into the picture. We make it so that you simply tell us what you want to discover and what you want deployed to what is discovered. And Ocari will continue to do that as devices come and go and as nodes come and go. So the same exact setup, but here we'll say the first step is installing Ocari. That's a simple Helm installation. Then the second step would be telling Ocari what you want to discover. So Ocari has 2 custom resource definitions. The first is the configuration, and that's where you tell Ocari what you want to find. And you do that by specifying what discovery handler you want to use. I mentioned previously we have 3 currently. The one in this scenario we're going to use is OnVIF because we're going to be discovering IP cameras. So you specify the name of the discovery handler OnVIF, not shown here. You can also specify some filtering information. Then you also specify the name of the workload. You specify the workload that you want deployed to each discovered device of this type. And we call that workload a broker. And so here we just set the image of our frame server that we were using earlier. So once you've applied your configuration to the cluster, Ocari will discover those devices and automatically deploy a frame server pod to each of the discovered devices. And it injects all the connection information for the specific device it's supposed to use in each pod. It also can automatically create services for you. It can create services to target specific devices and brokers or to target all of the discovered devices. So in this case, we'll say we specified that Ocari should create one service to target all of the devices, and we call that our configuration layer service, level service. So now the inferencing pod could point to one stable endpoint to get the output of all the frames of all the cameras. So the next thing we want to discover in our cluster is our GPU. So we'll deploy another configuration. This time we're going to specify the UW discovery handler. And not shown here, you would specify a UW rule to specifically select for the GPU. And as an image here, we're specifying our ML inferencing pod. So we apply this to the cluster, Ocari finds the GPU and automatically deploys the inferencing pod. We can see here, we're still at 3 steps, just like we were previously, but let's see how, if things change, you no longer have to take any further steps. So say you add cameras, Ocari automatically discovers them and deploys brokers. Say you add a node, Ocari automatically sees the GPU and deploys an inferencing pod. And the environment could continue to change and Ocari would continue to adapt. And so this is why Ocari really aims to be that interface between these clusters and these devices, abstracting away the details of how everything is changing. So now that we've looked at the motivation, let's go ahead and zoom into this green box here and look at the architecture. Also, feel free to pause me and ask any questions that you may have as I go, and just unmute and go ahead. But looking at the Ocari's components, Ocari has two custom resource definitions and a controller and an agent and discovery handlers. If we look at the first of those components, it's the Ocari configuration that we talked about earlier. In more general terms, you specify your discovery handler, you specify your broker, and you can give a name to the configuration. Once you've applied that to the cluster, the Ocari agent, which runs on every node in the cluster, will see that configuration, and it will look at that discovery handler and inform the discovery handler to go and start looking for those devices. The discovery handler will look for those devices, whether locally on the node or across the network. For each device it discovers, it will tell the Ocari agent, and the Ocari agent will create device plugins to represent each discovered device. It also creates an instance CRD, our second custom resource definition. It creates an instance to represent the individual device and that device's usage. So on that instance, you can see what nodes can see this device, what nodes are using this device, etc. Once that instance has been created, the controller will see it and it will deploy the specified workload that you set in your configuration to each discovered device. If we, sorry, go ahead.
Yeah, I have a question. So this example shows an edge cluster, but in the previous one you showed control plane. Does that control plane have to be at the edge, or it can be also somewhere else, like in the cloud?
Yeah, the control plane could be in the cloud. It doesn't necessarily need to be on the edge. Our controller runs on only one node in the cluster. That could be a control plane node, but it doesn't necessarily have to be. We kind of use that control plane terminology because it is more known for controllers to live there.
Got it. Got it. So essentially, if someone has a control plane in the cloud, they could have the Ocari controller running at the edge also, right? But the Ocari controller will still have to talk to the APIs, the Kubernetes API server, right? So there potentially there will be, like if there's like a network outage, it wouldn't be able to connect to it. So does the Ocari controller have some sort of retry mechanism, or maybe if you can't connect to the API server, it can like remain in standby? I'm just kind of thinking of like failure scenarios.
Yeah, totally. Those are really good points. And not just the controller, but also the agent has to reach out to the API server to watch for those configurations. And so this is a point that people have definitely brought up as we are focused on edge scenarios. And even KubeEdge was one put up an issue. Someone put up an issue about running on KubeEdge, which would doesn't have direct access to the API server always. We currently don't have a full-fledged solution to that of like caching requests and caching sends that we need to send to the API server, but it's definitely something that we want to look into further and flesh out our scenario for that.
Got it. Got it. Thanks.
I have a quick question about the discovery aspect of it.
Yeah.
I'm just wondering how it discovers. Does it do like an LSPCI? How does it look to see how does it discover the devices as they get connected?
Yeah, so that's dependent on the protocol. So for ONVIF, it'll do a general multicast on the WSD discovery service or expected port for ONVIF server URLs. But for OPC-UA, that's a different process of you can either contact the local discovery server to get those servers or directly just reach out to the discovery endpoints to see if they exist. And then for UDEV, that's just looking through the using UDEV to kind of enumerate the files in the local device file system. So it really depends on the protocol. Community members currently are working on ZeroConf, which is basically MDNS with a discovery service. So you would use ZeroConf standard discovery mechanisms. And then also co-op has its own way of doing discovery. So it totally depends on the protocol.
Okay.
So yeah, these discovery handlers can also be thought of as protocol implementations that just send back what they find and can take in some extra filters. And we'll look a little bit at that interface more in detail.
And then I had one more question about like, what are you discovering a specific type of GPU? Or like so far, what GPUs have you discovered? Like, are they, which manufacturer, I guess, is it specific to one GPU manufacturer?
So it isn't. In the UDEV rule that you can use with our UDEV discovery handler, you could specify the manufacturer name. I haven't personally played around with that. I don't know if you have, Yurka, but I know with, for example, with say you were trying to discover local video cameras, the kernel, the UDEV rule you would specify is like video, and then any video number 0 through 9. But then you could additionally specify an attribute of manufacturer name being, I don't know, what's a common, life cam or something like that, to narrow down the discovery.
Okay. I just wondered if it just, because I work with something similar that discovers NVIDIA GPUs, I just wondered if you guys could discover NVIDIA GPUs.
To add what Kate was saying, this obviously doesn't have like a deep integration into any specific device, unless you obviously write your own custom discovery handler and custom broker. And so, you know, we can discover any, like if we talk about local file system. So first of all the discovery, the idea there is we're not going to create Uber abstraction. Instead, we just rely on the discovery handler. Anybody can write however specific discovery handler they want, or use our generic one, such as the UDEV one. With the UDEV, yeah, Kate said it's a UDEV rule, and then you know you can tweak it how much you want it. But at the same time, you won't get the deep understanding of NVIDIA GPUs. Similarly, if you were to deploy an NVIDIA GPU device plugin. But what you know, so it depends how you want to use the device. If all you need is just to detect it and pass it in, then this will work. If you want to do some additional kind of a logic for the device, we have played with Ocari in a way where you can still use the native device plugin, so say the NVIDIA GPU plugin, and then use the Ocari, the plug and play functionality, where if the device is discovered, then Ocari takes care of deploying the broker pod spec. But the discovery itself is done, or you know, by the native plugin. So there's flexibility to how the devices are discovered.
Okay. Okay. So, all right. I'm getting the idea. So you'd want to write that some code yourself that was specific to NVIDIA if you were going to do this.
If you cannot detect it just as a like as a UDEV connected device, then you would want to write your own code. If it's good enough to say, you know, vendor, NVIDIA, a product ID, XYZ, then then you can just use the as is generic UDEV, and then write your own right broker, which will actually do the work that you want with the device.
Okay. Thank you.
But I think there might also be some pre-configuration steps that the NVIDIA device plugin does that Ocari's agent may not do on behalf of the discovered GPU. So there may be areas where more needs to be done, and maybe plugins need to be added to the agent for more complex device plugin scenarios. So that'd be really interesting to see and maybe take a deeper look into. But like Yurka said, we're trying to make it also that if you have an existing device plugin solution, you can keep using that, but still use Ocari for more dynamic devices, such as more IoT, traditional IoT devices like network-based ones. Great. So speaking of what we've been talking about, the device plugin framework, I just wanted to provide a little bit of background on it. For those who may not be familiar, it was released, I believe, in Kubernetes version 1.10, I think around 2017, 2018. And what it does is it allows nodes to advertise other node level resources or extended resources to the kubelet and the cluster at large. So traditionally, the resources that are available for pods to request are compute resources such as CPU, memory, and huge pages. What the device plugin does is it allows you to also advertise a device that could be requested by a pod. So you can see here that there's a GPU device plugin on each node, which was the motivating case for device plugin. And therefore, you could apply a pod with some container spec like this that would request, like he's mentioned, a NVIDIA GPU, and then that pod, some GPU pod, could be deployed to one of the nodes that have it. One thing to note here is that both of these nodes are identical in infrastructure. They both have GPUs. And that was kind of the assumption with the device plugin framework, was kind of cloud in mind, assuming that you had static system hardware that looked the same on most of the nodes. And it's pretty traditional to deploy your device plugins in a daemon set fashion. And so with Ocari, we're kind of removing that assumption. We're saying, hey, these devices may not even be in the node, and they may come and go across the network. And that doesn't change anything. We didn't modify the device plugin framework, but our instance CRD kind of handles those scenarios for us. And so looking a little bit into those custom resource definitions in detail, the configuration describes what should be discovered and what should be deployed to discovered devices. And if we look at its components, you have the discovery handler details, you specify the name of the discovery handler, and then all those details are what is the information that's passed on to the discovery handler. So some optional filters for IP addresses, MAC addresses, scopes. Then you have your broker pod spec, which is that workload that's automatically deployed to discovered devices. And this placeholder is where Ocari puts the device plugin resource name, so that that automatically deployed pod has requested that resource created by Ocari. And then we have our two levels of services, one for a stable endpoint to access a specific device's brokers, and one to access all of the devices discovered by this configuration's brokers. And then you can also optionally set some extra environment variables in all broker pods. So for example, say your broker needs to know a certain frame rate, you could specify that. And then a final thing to note is we have this capacity setting, and that capacity is how you tell Ocari how many nodes are allowed to use a device at once. Or you can think about it as how many workloads can use a device at once. And the second of our custom resource definitions is our instance. This represents the discovered device. Those broker properties that you set in the configuration and ones configured by the discovery handler appear here. So the discovery handler will see that the ONVIF, the IP camera, lives at a certain IP address, has a certain MAC address, and then we'll also get the device service URL, so that can be set in the broker pods. And also in the instance, you'll see that it'll show what nodes are currently using the device, and then also what nodes can see it. And the instance also specifies whether the device is shared or not. And shared is what we mean by whether multiple nodes can see it. That would be a network-based device, or an unshared device would be something that's local device, like a USB device or an embedded device. If we look more at the discovery handler model, originally, Ocari's discovery handlers were embedded in the agent. Like I mentioned earlier, we created a gRPC interface. So now discovery handlers can live outside of the agent in their own pods, which means that they can be implemented in any language of your choosing, so long as it supports gRPC. And we even created a template to kickstart discovery handler development for Rust. But what discovery handlers do is they go out and discover devices and report them back to the agent. And with our Helm chart, we deploy them to all nodes so that they're running along with the agent. And if we look at the discovery handler interface in a little bit of detail, you can see that it contains two services. The first of which is the registration service, and that's hosted by the agent. And so discovery handlers can come in and register with it and say, hey, this is my name, this is where I live, this is the type of connection you should make with me, and the devices I discover are shared or not. And that name is a direct mapping to the name that you specify in the configuration. So then, say the discovery handler has registered with the agent, then you deploy your configuration that uses the UDEV discovery handler. The agent will look up that discovery handler and look for the discovery handler called UDEV and call its discovery handler service, passing in the discovery details from that configuration. So the discovery handler service is hosted by discovery handlers, and in the discover request that the agent makes, it can specify those filtering rules. So like we mentioned earlier, for UDEV, say you were trying to find just USB video cameras, you would specify a UDEV rule like this. For installing Ocari, you could use kubectl and YAML to apply our components, but you can also just use our Helm chart. And breaking down that installation a little, if you just install Ocari in that first line, that'll install the controller on one node and agent on all of the nodes. If you set, then you can specify what discovery handlers you want to deploy. So here OnVIF, and you can even build your configuration with Helm. So here you're specifying that you want to create an OnVIF configuration with a certain broker image and a capacity of 2. If we kind of take all those components together and build it into a more full-fledged IP flow, IP camera flow, it would look like this. So in this setup, we have one control plane node and 2 other nodes. And say in this scenario, we have some custom application that wants to use all of the frames of IP cameras around this cluster. And it's been pre-configured to point to a configuration level service that Ocari will create. So the first step in this is deploying Ocari. So we use our Helm chart, we deploy Ocari. You can see in this scenario, we use that Helm installation that we had in the previous slide. So we have an OnVIF discovery handler has been deployed to each node, the agent's been deployed to each of the nodes, and the controller is running in the control plane, and our custom resource definitions are in etcd. The next thing we want to do is create a configuration, which was done actually in the same installation, Helm installation, but for this flow, we'll say that's a separate step. So in your configuration, here we're specifying we want to use the OnVIF discovery handler. And one thing to note here is we're specifying a capacity of 1. So we're saying that only one node can use this device at a time. So we apply that. And the agents now will start to look for, will now tell the discovery handlers to start looking for the IP cameras. We don't see any cameras, so nothing's happening. Let's say you connected a camera to the network. The OnVIF discovery handlers would see that, tell the agent, and the agent would create an instance to represent that device. And you can see here that both nodes have said that they can see this device. There's only one slot because we set capacity to 1. And so only one of those nodes will get to use the device. The controller will see the instance and select one of the nodes, and it will get the broker to now start using the device. And now our custom application is getting all of the frames that it wanted. However, what happens if a node goes down? So the controller will see that the node went down. And since the other node said that it could see the device, it simply will redeploy that workload to the other node. However, there was a little bit of lag time there when the custom application wasn't getting any frames. So if you wanted to create a more highly available scenario from the start, you could have set a capacity of 2. So just highlighting the change here, it was right there. You could have, instead of 1, set the capacity of 2 when installing the configuration, or you could update your configuration. And then from the start, there would have been 2 usage slots. Both nodes would have been using that camera. And so if the node went down, it's fine. The other node still has a broker that is using that camera. Great. And now I was just going to show a demo. So in our demo, same scenario we've kind of had been talking about through the presentation. We'll have 2 nodes. Both of them are Intel NUCs. And we're going to have connect them in a K3S cluster, and we'll deploy Ocari using Helm. So I'm just
Can
gonna,
you, I have
yeah,
sorry,
go ahead.
I have a question. Can you go back to the previous one? Yeah, that one. So the broker is actually an actual pod or Kubernetes pod in this case, or?
Yes, so the brokers are always pods, and you just specify the image. It's actually a pod spec that you're building in the configuration,
Mhm.
but you're only applying the image part of it.
Got it. And then in terms of like if you have a GPU in this case to do some inference, that will be a different pod, right? Attached to a GPU device.
Yes, exactly. But that brings up a good point, and one of the requests from the community. What if you could have one broker that's targeting two devices? So what if in our initial scenario, we had one broker that was connecting to 3 IP cameras and 1 GPU?
Mhm.
So that's something that we want to support, and we call that a deployment strategy. Right now, we have a microservice approach for our deployment strategy of one pod per device. And so that's kind of in our roadmap to come.
Got it. Got it. That makes sense. Thanks.
Awesome. So I'm going to voice over this demo. And all right. So like I mentioned in the diagram before, we have two nodes in our cluster, and we're using Kubernetes dashboard to kind of visualize what's happening. But if we were to go into terminal, you can see the same thing. We have our two nodes. And so our first step here is to go ahead and install Ocari. And we'll do that with that. First step actually, sorry, is to grab our Helm chart. And then we can now go ahead and install Ocari. And this is similar to that command that we saw earlier. So we're specifying onVIF and we're building up our configuration. And we're setting a capacity of 2 because we want each node to be able to use the discovered cameras for that high availability scenario. And so we're applying it, and then we're going to go back into the dashboard, and we'll see if we go to our custom resources now. Just 9 seconds ago, the instance and configuration CRDs were applied to our cluster. If we look in, we'll see that we do have that one configuration that we created with our Helm installation. Looking at some of the details of it, you can see that image we specified in our Helm installation is going to be our broker pod. And you can also see that we set a capacity of 2 in our Helm installation. And then you can see there by default, we create configuration services and instance services. Those are what we call the 2 services we create to target individual brokers and then all brokers of a certain configuration. And then you can also see how we specified what discovery handler to use. So we specified onVIF and those discovery details. Great. And going back, we'll see that if we go into instances, there's nothing, because right now in the demo, I haven't plugged in any cameras yet. Now, if we go and look at what pods were automatically deployed, we can see, as expected, we have an agent running on each node and an onVIF discovery handler running on each node and 1 controller running. So at this point, I'm going to go ahead and I plugged in a camera. And so we'll go ahead and look at the instances. And wait a second for that to come up. So right now what's happening is the onVIF discovery handler will see it, and it'll see that there was a change in what devices were visible, and it will tell the agent will create the device plugin to represent it and this instance. So you can see in the instance details that the specific IP address for the camera that was discovered, the service URL, and you can see that both NUCs can see it and that both NUCs are using it. And so we're confirming that here, that we have this broker pod was now deployed to each of them just a few seconds ago. So now if we go to our services, we'll see that we have 1 instance service created and 1 configuration service. So to better visualize this, we're going to deploy a streaming application that is going to display all the frames from those 2 services. I'm clearly talking faster than I intended. And so now we're gonna get the node port of the streaming application so that we can just port forward it to see it locally. And you can see here, we're confirming that streaming application is running. If we go ahead and go, we'll see, okay, we have these 2 images in our application. The top one is displaying the output of the configuration level service, and the bottom one is pulling from each instance service. This is obviously footage of the setup we have here, a switch and 2 Intel NUCs there in the right. So let's go ahead and plug in another camera, and we'll see another instance level service pop up over here. So if we go to our custom resource definitions, we'll see another instance pop up momentarily. There it is. And then if we go back to our demo and refresh, this streaming application is very naive. It's just a Flask app. So the frame rate's only 1 frame per second, but you can see now how the top level service is now round robining, and we have another new instance level service that dynamically popped up when the device was plugged in. And so we were able to show that devices can dynamically be discovered. Also to show that devices can go away and Ocari can adapt. I'm gonna go ahead and unplug one of the cameras. One thing to note is we have a 5-minute grace period for shared devices. We wanna make this configurable in the future. So after 5 minutes, I just jumped ahead. You can see that now, once again, we're back to only having one stream. And then just to close up, as with most Helm installations, you can just do a Helm delete Ocari and everything will be brought down. And so just to confirm that, if we go into our Kubernetes dashboard and look at the pods, you can see that they're all terminating. Great. Just talking a little bit about a timeline. Ocari is fairly young. We launched and went open source in October of 2020. We from then had a Kubernetes Slack channel, #Ocari. And then we kind of focused on community engagement. I had some speaking opportunities, went to some conferences. In January, we added OPCUA. When we launched, we only had UDEV and ONVIF. And we started doing community calls. Then in April, we added our new discovery handler model, wherein they don't have to live in the agent, and we abstracted them behind a gRPC interface. Then in May, we participated in KubeCon EU, having an intro session and a lightning talk. And then right now, September and October, we participated in Gracehopper Open Source Day, and we just got accepted into the CNCF. So a lot of the work right now is transitioning over, putting ourselves in a new repository, et cetera. And in next week, we're presenting at KubeCon at WASM Day. We did some cool investigation into what if Ocari was a WASM application, and what if it could help expose IoT devices to WASM apps running on Kubernetes using Crustlet. So a lot of fun there, an investigation, and a pretty cool talk to check out. And what's to come, we'll reiterate this a little bit more in the next slide, but we really want to build up our community and get to a point where there's some steady contributions coming in from community members. And we really want to support more discovery handlers. The more discovery handlers Ocari supports, the more that we can discover and expose to Kubernetes clusters. So reiterating that in our roadmap, that's definitely an area we want to focus in on. And we also want to focus in on deployment strategies, like we talked about a little bit earlier, making it so that brokers can target multiple devices at once, multiple devices of different types, make it so that brokers can be jobs rather than longstanding pods. And then, like I mentioned, we really want to grow our community. To give a little perspective on what the community looks like now, we have 18 contributors. About, I would say, 4 consistent maintainers. We have a larger number, but that are contributing fairly often. 660 GitHub stars, if that's a metric that you enjoy. And we have 159 Slack members, which I think in May we had around 70. So that's really shot up, and it's been cool to see more participation there. And for resources, if you want to learn a little bit about Ocari, we have our documentation site. We have some demos there that you can try out, and we even help you mock some IoT devices. And we have some documentation on how to get started contributing. And of course, our Slack and monthly Zoom calls where you can more actively engage. So with that, any questions? And love to discuss any points a little further too.
All right. Yeah. Great presentation. Great demo too. So you also have a plan eventually to, I mean, as the community grows, to go into incubation, I would imagine, right? So.
Yeah, definitely would love to get to incubation and possibly beyond to graduation. Obviously, right now we're kind of focused in on Sandbox and being where we are and hitting those goals of growing our community. I think one thing that's interesting about being here with the runtime tag is there's the whole landscape map, and part of that Sandbox project is finding where you fit. And I would be curious y'all's perspective on if you think runtime is the part of CNCF where Ocari best fits.
Yeah, I think so. I mean, this is it falls within the scope because runtime, looks at different types of workloads, and one of the main ones has been, how do you run these at the edge, right? So, and basically integrating with things like K3S or Cube Edge, right? Or I think there's some other projects too, like OpenYurt, and there's also another one called Super Edge. So there's a few projects that are around how do you run workloads at the edge, and yeah, and they're all like actually presented here, and then they fall within the scope.
That makes sense, definitely.
Yeah, so another thing, so it was actually brought up by the K3S team that, if the community wants to get together so they can actually tackle a problem. So we have this idea or entity called working groups. So they actually fall within the tag. So it's just a matter of the community getting together, the projects, working together, and then coming up with a charter, and then they can, set up regular meetings and, look at problems, look at architecture, roadmaps, and work that way under the umbrella of the CNCF. And then the CNCF facilitates and helps with, things like promoting, events at KubeCon and the website and all the different channels that they have. So I think the Ocari maintainers can actually reach out to, or maybe you already have reached out to the K3S team, and maybe, you can talk about it, or maybe you can create a working group. And I think the next step for that would be to, after talking about it, will be actually creating a charter, right? And then just getting a charter approved and just, getting started, right? But I mean, it's more about like community work and, maybe coming together and seeing what problems you have, and seeing if you want to come up with some standard, that makes it easier for end users. In the end, is how do you make it easier for end users?
Totally, that makes sense. And I think it'd be interesting to think about what that working group sphere would be, since there is the IoT Edge working group. But they do seem to focus a lot on the device and the compute on the edge, while this would be interesting to focus on the IoT devices that aren't necessarily the nodes, or maybe just the interaction between those two.
Yeah.
And
where does that actually fall under the IoT device working group? Is that under the Linux Foundation or what?
I think, let me see, I have it under,
So, well, we're under the CNCF, so it's more like cloud native. So anything related to cloud native. So there might be some overlap, right? So,
oh, I think it's Kubernetes. It's on like Kubernetes on their Slack. They have the IoT Edge working group.
oh, okay, okay. So that's so it's under Kubernetes, yeah. So, yeah, so there's an overlap there. So, I haven't reached out to any of those folks. So, but maybe I mean, they can come together. I mean, if that's the right place to work, then it's fine, right? So, but then in terms of tag runtime being here, then it's another channel, right? So, but hopefully there isn't a lot of overlap, right? So I mean, we're tackling different problems because the idea is just getting the community together is to to agree on problems that make it easier for end users, right? So that end users at the end are not confused about what to use or where to go to or what standard to use.
Totally, that makes sense. And so it sounds like there's some working groups within Kubernetes and then also within CNCF.
Correct, yeah.
Great, yeah, we'll definitely be in touch with the K3S folks and kind of think about if it is joining in on the Kubernetes one, or maybe if we feel like we need a separate space to discuss and work together.
Right. So yeah, and the CNCF will be more general. With Kubernetes, it was just targeted specifically for Kubernetes, right? So if you want something more general, I think it will be more of the CNCF. But it's up to you. It's how the community wants to go forward.
Great,
Right.
great.
Thank you. Anybody else has any other questions? Or I think we lost everybody. So I think Alina is there, but maybe she's not around. Okay.
Yeah, just wanted to say thank you. I was driving mostly for the during the meeting, but yeah, I'm looking forward to learning more about the project.
Awesome, thanks.
Thank you.
All right, thanks.
Sounds
Yeah, let's keep in touch. Have a great day.
great. You all as well.
Bye.
Bye.
Thank you.
Bye.
Bye.